This is the first lecture now that we've cast Maxwell's equations into matrix form on the Yee grid, this is the first lecture where we can pull this together now and model something. In this case, we're going to be calculating the modes in arbitrary waveguides or transmission lines. The examples I'm going to be using in here are dielectric waveguides, but they could be metallic rectangular waveguides or microstrip transmission lines or just about anything. This is not a method that we are going to implement in class. However, all the information you need to implement it is here. You could certainly do it as a project, but the point is, all the information is here. So, before we begin, we need to actually understand a little bit about waveguides and modes in waveguides. From there, we're going to derive a fully rigorous analysis of waveguides. It's rather computationally intense, so if you're on a moderately sized computer, there will be a limitation to how large a waveguide you can model. But these days, most computers, you can model about any waveguide there is without any problems. Then we're going to step through some approximations where we can sort of do the rigorous full vector waveguide analysis. Can't call it rigorous anymore. We're going to make some approximations, but it's going to make our formulation analysis a lot simpler, computationally more efficient, and we're going to get just about the same answer. And we'll call that quasi-vectorial analysis. Then we're going to move on to a slab waveguide. It's a very simple geometry, but useful for a lot of things, and you'll see more of that next semester if you take the follow-on class. Then I just want to touch on some simple implementation details in MATLAB. So our first subject is electromagnetic waveguides. The first concept in a waveguide is something called total internal reflection, and we have talked about this before, but essentially we have a wave coming in at an angle from something with a high refractive index to something with a low refractive index. And we see that the wave refracts, and it actually ends up having a larger angle in the second material. So it makes sense then, as we come in at a larger and larger angle, that the refracted wave is going to come closer and closer and closer to being parallel to the interface. Right when that is parallel, in fact, the incoming wave would be along this red dashed line. We call that the critical angle. So in fact, any angles greater than that will completely reflect. Nothing will transmit because we're past the critical angle. And so that's what's illustrated over here. We're coming in at an angle greater than the critical angle, and it completely reflects. From previous lectures, you will know that there will be a little bit of a field out here, but it's evanescent and decays very quickly. So the next thing, we'll look at a slab waveguide. So kind of like the transfer matrix method, what we're looking at here is a cross-section of three completely infinite slab layers. And this layer N2 in the middle will have the higher refractive index, so it's higher than the refractive index on either side. That's the necessary condition to have total internal reflection, or have this critical angle. So if we have energy that's propagating at an angle greater than the critical angle, then it will have to stay guided in this medium. And so this layer we'll call the core of the waveguide. The other two regions we'll call the cladding. And now we have a waveguide, in this case a slab waveguide. But it's total internal reflection that is really producing the waveguiding effect. Now there's one more thing. The wave inside this guide, we think of it as bouncing around. Well, we need to look at the round trip phase. So we'll pick a point here on the wavefront, and we come back to essentially the same point. It turns out the phase of the wave between these 2 points has to be an integer multiple of 2 pi. If this is not the case, then the wave will interfere with itself, and in fact it'll just leak out of the guide. It actually won't be a guided mode. But because of this rule, we only have certain angles that will be supported in this guide. And this is really the origin of what we'll call modes. There are only certain electromagnetic configurations that we can consider modes guided in a waveguide. Anyway, based on the angle sine theta, the wave, since it's bouncing around, it travels at or apparently travels at a slightly different speed And we characterize that through an effective refractive index, which is not necessarily the refractive index of any of the materials. It's just that we look at the wave that's being guided and it appears to be moving along at a certain speed, we'll characterize that speed with the effective refractive index. And then we can also calculate the propagation constant from that. We'll talk more about what that means too. So we just finished talking about waveguiding from a ray tracing perspective, and that's a good hand waving argument. We can get a pretty good intuitive feel of what's happening, but we really need to go to Maxwell's equations and ask them what is happening. In that case, if we model the same slab waveguide but use Maxwell's equations, here is what the first 5 modes look like. We have what we call the fundamental mode, and we know that because it has 1 hump. Second order mode, there's 2 humps. Third order mode, there's 3 humps, 4 humps, 5, and so on. Now, when we analyze a waveguide, we're actually going to calculate many modes. But it turns out only a few of them are guided. At some point, we get to high enough order mode, it's no longer guided, and it's going to look strange, and we'll see that, and it's no longer considered a guided mode. But these are what the modes actually look like. This is a rigorous solution, and in fact you can use this to benchmark your codes if you ever write a waveguide analyzer. So the core here is 3 wavelengths wide, 3 free space wavelengths wide. I used a refractive index of 2.0 for the core, and then I just use air for the cladding regions. So it's basically a thin sheet of glass that guides. There are 2 types of waveguides. We can talk about a slab waveguide, which is similar to the infinite slabs we had in the transfer matrix method, where we have some infinite slab here that we'll call the core, and another infinite slab here. So in fact, there's only confinement along this vertical axis. Within this plane, waves can go in and out of the board, or they can go left and right, and they're free to do that. There's only confinement in one direction, and we call that a slab waveguide. We also have a channel waveguide, where there's confinement now along 2 axes. So in the third axis, in this case in and out of the slide here, it's free to travel. So this is acting much like a pipe. So confinement in 2 directions and free to go in and out of the board here. So we call that a channel waveguide, slab versus channel. Just some examples of what realistic waveguides look like. In integrated optics, where we're making little tiny light chips, we use a bunch of different ways, but the rule is we need some high index dot, if you will, surrounded by a low index outside. And there's a bunch of different ways, and we typically use photolithography to form various different types of waveguides. There's also a different type of guided wave, more similar to slab waveguides, but these are surface waves, where there's some kind of phenomenon that is not sandwiched between 2 interfaces, but somehow stuck to one interface. But these are analyzed just like waveguides. I'm going to throw them in here. Some electromagnetic folks would argue this is not a guided wave and doesn't belong here, but it's analyzed the same way. It confines energy, and in some way I consider surface waves very similar to a slab waveguide. But there's various types here as well. Here we have some metal type waveguides for radio frequencies that you're probably a bit familiar with. Just a standard wire is a waveguide, in fact. And of course there's the old twisted pair, the old phone lines, that's a waveguide. Of course the rectangular metallic waveguides, the coaxial cables that used to go into televisions, now it's all HDMI, but we used to have coaxial cables. That is a waveguide. Then there's waveguides that you see on circuit boards, and we use these a lot of times for very high frequency signals. The most common one for sure is the microstrip, and it's called a transmission line, but a transmission line is a waveguide. A waveguide isn't always a transmission line, but all transmission lines are waveguides. The difference is transmission lines have at least 2 conductors, and once they have 2 conductors, they can support a mode all the way down to DC. Whereas like the rectangular metal waveguide, that's not going to conduct DC. There's a cutoff frequency below which it doesn't guide anything. Parallel plate waveguides, strip line waveguide. Think of this as a microstrip, but had to bury itself down into the circuit board. Then there's also slot lines and coplanars, and these are pieces of metal on a substrate, and your field forms between these metal pieces here. And they all have their advantages and disadvantages, but I don't want to turn this into an electromagnetics theory class. I just want to set you up so you can model these types of things. Okay, so that is our brief introduction to waveguides. Now we're going to go to Maxwell's equations, and we're going to see how to pull all these together, use all the stuff we did with finite differences and the Yee grid, and this is a really good illustration of how we can very simply formulate a really sophisticated code, and it's actually quite easy. And this is doing a fully rigorous analysis of waveguides. So no approximations will be built into this yet. We start off with our typical place that we talked about in one of the first few lectures when we were talking about preparing Maxwell's equations. So we start here, and to remind you what has happened, we're using a normalized magnetic field. We've also normalized our grid, and we've also assumed just diagonally anisotropic materials. But this is our very, very typical starting point. No approximations really have been built in, other than at this point we're assuming diagonally anisotropic materials, but almost all waveguides just contain standard isotropic materials, so in fact we can use this without an approximation. If there is anisotropic materials, this needs to be modified a bit. The next thing we need to do is learn what our mode solution looks like. What will the answer look like? This isn't the exact answer, it's just the form of the answer. So first, let's look at a waveguide. So I drew a very strange arbitrary waveguide, and obviously it's heading off in the z direction, so the power is going to be propagating along the waveguide. And in fact, the field propagates with this propagation term, e to the gamma z. Gamma is going to be, we call that the propagation constant. It's a complex number, so it has potentially oscillation and decay associated with it. But let's look at the cross section. If we look at the cross section, what we see is that there's a bunch of energy confined here that fits inside the waveguide. Now, this cross section, this amplitude profile, that never changes. That stays nice and constant as that mode propagates down the waveguide. The only thing that happens as it propagates is that this accumulates phase, or perhaps decays or grows, according to the exponential term. So in fact, the overall total electric field anywhere in the guide can be written this way. Here's the total field. It's written as an amplitude term, which is describing what the field looks like in the cross section, and then a propagation term, which describes phase or decay and growth. If it's a lossless guide, which is a good assumption, then this is really just going to describe accumulation of phase. The last concept on this slide is all waveguides are three-dimensional. When we are calculating modes in a waveguide, another built-in assumption is that the waveguide is uniform in the z direction. So when it's uniform in the z direction, in fact, all we really need to do is look at the waveguide cross-section. So in fact, all waveguide analysis, when we're calculating modes, comes down to just a two-dimensional analysis, which is really, really good news. Okay, so we're going to go grab the first of our Maxwell's equations. So it's one of the equations that came out of the curl of E equation. And now we have the form of our solution. So we plug in the form of our solution for the different field components. We plug that into this Maxwell's equation, and we turn the crank on our algebra, and out comes a new equation. It no longer contains E and H, it contains A and B. Remember, those are the amplitudes. We still don't know what they are, and we're going to calculate those, but we just have A and B, the amplitudes, and our Z derivative has dropped out, and become gamma over k naught. Now that happened because we know what the field's doing in the z direction. It's just accumulating phase. So that derivative is replaced with gamma over k naught. Remember, gamma is that complex propagation constant. So lessons learned from the last slide is that our final equation was the same as Maxwell's equation with these following differences. All the E's are replaced with A's. All the H's are replaced with B's. And all of our derivatives in the z direction are replaced with a gamma over k naught. And we're going to call this a normalized propagation constant. So given this, we can go to all 6 Maxwell's equations and do those change of variables. And here's our final set of 6 equations. Remember, we're going to use this normalized propagation constant now. The normalized propagation constant is related to the effective refractive index through this equation. And remember, the effective refractive index is a complex number. It has an ordinary refractive index describing the speed of the wave, if you will, and an extinction coefficient, which describes the decay or the growth of the wave, if there's any loss or gain in the materials. So here's a great slide, and here are the 6 equations that we had on the previous slide, given everything we know about how we're implementing the finite difference method and how we use the Yee grid and express the fields on the Yee grid and derive the finite difference approximations, etc., we can jump immediately from these differential equations to those differential equations now in matrix form. Each of these lowercase letters are column vectors. So for example, the one that I'm circling now, a sub z, this is a column vector containing the az component at every point throughout this 2-dimensional grid, which is the cross-section of our waveguide. A sub y is the y component, a sub z is the z component. And the same for bx, by, and bz. Those are the amplitudes of the magnetic fields now. We recognize our derivative operators. These are banded matrices. So this is going to perform a first-order derivative in the y direction of the a sub z component. Our mu sub xx, hopefully we'll recognize, is going to be a diagonal matrix. A diagonal, but it'll be a square matrix, and multiplying this column vector. So we jump immediately. We actually don't have to touch any finite differences. They're hiding behind the curtain, if you will. We're going to write this function that calculates those banded matrices. So you just tell it the size of the grid and the resolution. It calculates those matrices. It's very easy to diagonalize your materials arrays, and so we can immediately build those equations. Now for waveguide analysis, all the energy is trapped in the middle of the grid. So by the time we get to the edge, the fields should be very, very close to 0. So this is a great place to use our Dirichlet boundary conditions. And in fact, that's the boundary condition built into these derivatives. It's not the only possibility, but it's the one that we're going to use here. Now this theme comes up very frequently in computational electromagnetics. We expand Maxwell's equations into the 6 component equations. We jump to matrix form. We solve now for the longitudinal components. We substitute that back into the remaining 4, put that in matrix form. That came up in transfer matrix method. It's going to come up here. It'll come up again in rigorous coupled wave analysis. It'll come up again in method of lines. So it's a very common manipulation. So we have our 6 matrix equations. We're going to solve the 3rd and the 6th for the longitudinal components, BZ and AZ. Then we're going to take this BZ term, this expression for BZ, and eliminate BZ in these 2 equations. We're going to take this expression for AZ and plug that in up here to eliminate AZ from those equations. So here's where we do that. Now we're left with 4 equations. Here's our 4 equations. They no longer contain AZ or BZ. They're only containing the transverse field components, the EX, EY, HX, and HY, which in fact we're expressing as AX and AY, BX and BY. So all we're doing here now is rearranging first the order of the equation. So this equation will end up here, and our first equation will end up being second. So we swap the order, and we're also rearranging terms. So we just did a little bit of algebra on this. We're bringing the gammas over to the right-hand side for both sets of equations. Those are our normalized propagation constants. And everything else on the left, we've collected coefficients on bx and by. And down here we collected coefficients on ax and ay. But it's those remaining four equations now with az and bz eliminated. So these two sets of two equations we can now write in block matrix form. So these two equations become this block matrix equation. And these two equations become the last block matrix equation. And we're almost to this PQ form. So here is our good old PQ form. We have the two block matrix equations we had on the last slide. We're going to take this first big ugly square matrix and call it P. We're going to take the second big ugly square matrix and call it Q. So we are recasting now our two block matrix equations this way. And so here's a reminder of what P and Q are. But now we've reduced our matrix equations to this. A lot simpler to write and to manipulate. So we're going to take one of our equations that had Q in it, and we're going to solve it for this column vector containing bx and by. So here's bx and by. We're going to go grab our second equation, and we have bx and by here, and we have now an expression for bx and by that we can substitute in here. So we do that, and what we've done is eliminate bx and by. We now have a single matrix equation that only has ax and ay. And in fact, this is a standard eigenvalue problem. We're going to call P times Q an omega squared. So omega squared is PQ. And that is a generalized eigenvalue problem that once we build the omega squared, we can solve with one line of code in MATLAB. So here's a little bit of an aside. Here's how you would make an optical waveguide, a rib waveguide. We start off with a silica substrate. So in practice, this is going to be a circular plate of glass. Kind of looks like a little frisbee, but it's perfectly flat. And I'm just showing a little piece of it here. You put it on what's called a spinner, and it spins at several thousand RPMs, and you pour, actually I'm sorry, that's another step. So we have this substrate. We're going to grow a layer of something with a high dielectric constant, or high refractive index. Now here's where we put it on a spinner, and it spins at several thousand RPM, and we pour something on it that pours like pancake syrup that we call a photoresist. And it's spinning so that it spreads itself out evenly over the spinning wafer, we call it. Then we do a process where we put a mask over this that will shadow certain regions. So let's say it shadows the center region, and we expose it to light. Now suddenly, where the light did not get absorbed, the resist will wash away in a developer solution. So we develop it, and we're left with a standing portion of our resist. Then we etch it, which bombards this with high-speed ions that etch away the material. But in the center, it's being protected by the photoresist. So we etch until our resist is maybe almost gone. So we've etched out here and etched over here, but we have not etched here because it was protected by the resist. Well, then we can dissolve away all of the resist, and we're left with what we call a rib waveguide. So it's just the fact that these are our techniques for making things at the optical scale. This is the micro scale, and we use lithography, and that is really what dictates the geometries of the waveguides. We'd like to do more, but we're a little bit restricted on what can be done, or at least what can be done cheaply. So we throw that waveguide into our model, and here's the modes that come out of the rib waveguide. And these are fully rigorous models. And what we can see is that we have a fundamental mode. And so here's our fundamental mode It has the highest effective refractive index. Our next order mode looks very much the same, but notice how this is polarized. Almost completely linearly polarized left and right. Now this is almost completely linear polarized up and down. We look at our next order modes. It's obviously some kind of second order mode because it has two humps. But this one is, for the most part, linearly polarized left to right. You can start to see a little bit of tilt here. And this is mostly polarized up and down, although you can see a little bit of tilt in the fields here where they're not purely up and down. That's going to come up again later when we talk about quasi-vectorial analysis. So here's some final notes. For channel waveguides, energy is confined along two axes and free to propagate in the third. Modes in channel waveguides always contain all 6 field components: Ex, Ey, Ez, Hx, Hy, Ez. There's no way to justify canceling any of those terms to exactly 0. Now, having seen the modes on the last slide, how linearly polarized they are, we can see that there are some field components that are going to be extremely small. And in fact, it becomes a good approximation to set those to 0, but it does require we have some a priori knowledge that they will be close to 0. So the conclusion is, and in all texts they just present TE and TM modes and waveguides, and channel waveguides, they don't exist. There is no such thing. However, they are very good approximations. So what we're going to do is, rather than call them TE and TM, we're going to call them quasi-TE and quasi-TM, just to remind us it's an approximation, it's not a real physical thing. Channel waveguides don't support TE and TM modes. They only support what we call hybrid modes, which really just mean they have all 6 field components. So with the lesson that it is a good approximation to cancel some of the field components, how does this reduce our matrix equations? How much speed improvement do we get? What difference in the answers are there? So let's go back to our original eigenvalue problem where we had an omega squared, and I've repeated that here. There's 4 elements in this matrix. There's an omega squared xx, an omega squared xy, omega squared yx, and omega squared yy. So if we work through the linear algebra and the matrix algebra, here's how the expressions look for all 4 of those field components. Or I'm sorry, all 4 of those matrices in the omega squared matrix. They're big, they're ugly. And we don't have to calculate these for the fully rigorous analysis. That just falls out of the math. But we need to look at them now. So let's think about this. We have a block matrix equation which really represents a set of 2 matrix equations. So here we're going from our block matrix equation to our 2 separate matrix equations. Now let's think about physical meaning behind this. If we think of this equation as an equation for a sub x, we see that it is coupled to a sub y through the omega xy term. So we'll call this a cross-coupling term. It's the reason that there is always an ax and ay, because they're coupled. They always have to be that way. This is a self-coupling term. And likewise, we can have our second equation. We would call that the equation for ay. We have a self-coupling term, but we have another cross-coupling term, meaning you can't have an ax without an ay, can't have an ay without an ax, because these terms are here. And there's no analytical way to say those are always exactly 0. But what we can say is, having seen some of the modes and saying, you know, they're pretty darn independent, maybe we could set those cross-coupling terms to 0 as an approximation. And so that's exactly what we do. So let me make an argument here that these modes are strongly linearly polarized. So rather than show the vector nature of the field, I am showing the x and y components separately. So here on the top is the first order mode. Here's the x component, And then on the same color scale, here's the y component. And I'm not sure how well you can see this, but there's a little dot of red there, and we can see a little bit of red here and there. But for the most part, this is much, much, much smaller than EX. So what I did is I took the ratio of EY over EX and plotted it on a dB scale, although for some reason it's not showing dB there. And what we can see is it's really, really darn small. So the EY component is much, much less than EX. The only time that it seems like it's a large number is out here where there really isn't much EX anyway, and it's just more of a numerical artifact. But we can definitely see where there is an EX, the ratio is extremely small. We can look at the second order mode and do the same thing, and we see that the ratio is very small. This tells us there is still an EY component, absolutely. And to be rigorous, we can't ignore that. But the point is, it is much smaller, and it is a good approximation to assume that there is no cross-coupling. So if there is no cross-coupling, we're going to cancel these cross-coupling terms. And now our two matrix equations reduce to these two things. We have a eigenvalue problem with just AX and another eigenvalue problem with just AY. And just to remind you what the omega XX was and the omega YY. So we solve these equations, these two, and we always are going to have to solve both now. Before, they both came out of one analysis. Now we actually have to perform two analyses. But in fact, it's quicker to perform two of these smaller analyses than just one of the bigger ones before. So it's a more efficient analysis for sure. So if we do this, here are our modes. And what you can see now is that they are perfectly linearly polarized. And why is that? Because we canceled the cross-coupling terms. Let's actually compare now the full vector analysis to the quasi-vector analysis. So in the full vector analysis, we saw there was a little bit of bending of fields here, a little bit of bending of the fields out here, and we looked at the effective refractive indices that we calculated. Now we go to the quasi-vectorial. Well, since we're ignoring the cross-coupling, now it appears that it's perfectly linearly polarized. We don't see any warping, so that's one little tiny difference. But let's look at the effective refractive indices. This first one looks the same, second one looks the same, third one looks the same, and finally at this fourth order term, we see a little bit of a difference. And in fact, the higher order the mode, the more significant the cross-coupling, the more important it is to consider. And so that approximation tends to break down. However, fortunately, most waveguides, we really just want to be single mode, only support a single mode. And it's a really, really good approximation for that first order mode, for sure. So in this case, we did a full vector analysis. It took 12 seconds for a given grid resolution, lambda over 30. Quasi, remember we're running two simulations now, so they each took 3.5 seconds, overall 7 seconds. So we almost halved our run time, and the answers we got are so close to the original that it's really hard to justify even doing the full vector analysis. Unless there's something we know that we have to account for that we know won't come out in a quasi-vectorial analysis. It almost doesn't even make sense to do that. So I want to leave you with this. Quasi-vectorial analysis is an approximation. TE and TM modes do not exist in channel waveguides. So we're going to call them in this class quasi-TE and quasi-TM. But hopefully in these slides I have justified that it is a very good approximation. This is one of the things when I was taking electromagnetics drove me absolutely crazy, and I didn't understand it. And every time I asked the question, in hindsight now I know it's because the professor didn't understand it either, because all the textbooks just say, here's a waveguide, we're going to solve for the TM mode, and these field components are 0. And it's never justified why those are 0. And the answer is there is no justification. It has to come from a priori knowledge. We calculate the modes and see that they are very close to 0. But it is an approximation. But the textbooks don't present it as an approximation. They present it, this is a TE and this is the TM mode. Okay, on to slab waveguides. And we're going to reduce our analysis down in dimensions to just one dimension. So analyzing slab waveguides is very fast and still very useful. But for this configuration, we can reduce Maxwell's equations down without an approximation, simply because the geometry is simpler here. We have a slab waveguide, not a channel waveguide. So we start off with the same set of 6 Maxwell's equations. There's a difference now. If we have our coordinates defined relative to the slab waveguide this way, the y direction is perfectly uniform. The wave is going to travel in the z direction, so there is no accumulation of phase in y direction. The materials don't change in the y direction. So in fact, any derivative we take in the y direction has to be 0. So we go back to Maxwell's equations. Anywhere there's a y derivative, we're just going to cross it out and drop it. And now we have this reduced set of equations that's valid only for slab waveguides with a wave traveling in the z direction. What we see from those remaining 6 equations is they've actually decoupled into 2 independent sets of equations. One we're going to call the E mode, because we're going to eliminate all references to B and end up only with A. And the other one we're going to call the H mode, because we're going to eliminate all references to A and only have a B left in there. So for the E mode, we're going to have a wave equation with only A. And for the H mode, we're going to have a wave equation with only B. So using what we've learned about finite differences and how we implement it, we can jump straight from our differential equations to the matrix form without explicitly touching any finite differences. That's very cool. So we make the jump, and now we have our 2 sets of matrix equations in matrix form. So from these 2 sets of 3 equations, we can derive a wave equation. So what we'll do, we'll take our first set of 3 equations, look at the last 2 and solve them for the bx and bz components. Now we have expressions for bx and bz. We can go back to our first equation and put those expressions in for bx and bz. So now we have a matrix equation that only has ay in it. And in fact, we've arrived at our eigenvalue problem for ay. We do the exact same thing. We take our 3 equations for the H mode. We take our second 2, solve them for ax and az, then put these expressions in the first equation to replace ax and az with by, and we have an eigenvalue problem for by. So we have 2 modes supported by slab waveguides, and they can behave differently, simply because the fields are oriented differently, they're seeing different boundary conditions, the energy distribution is a little bit different, but both have the form of a generalized eigenvalue problem. So 2 modes in a slab waveguide. So here's another example. You can use this to benchmark your code if you write one. We take the same slab waveguide that's 1.8 wavelengths thick in the core. It has a refractive index of 2.0 in the core, a refractive index of 1.5 in the cladding, and we take the same exact slab waveguide and calculate the E and H modes, and here's what we get. So these numbers are the effective refractive indices. Notice they're a little bit different than the E modes. The E and H modes are definitely different. So this is a great way to benchmark your codes if you choose to write these. Some final remarks about slab waveguides. For slab waveguides, energy is confined along one dimension and free to do whatever it wants to in the other 2. So we notice we restricted propagation to the z direction in the slab waveguide. But if you imagine rotating the slab waveguide, after you rotate it, if all those layers are of infinite extent, it still looks the same. So in fact, we can analyze a slab in the z direction, and those results apply to any direction. Another bullet that you need to come away with here is that Maxwell's equations decoupled into 2 modes. This happened when we did the quasi-analysis, but we used an approximation to split them there. Here they rigorously decouple into 2 distinct modes. So in slab waveguides, there actually are two modes in that. Channel waveguides, we artificially did that. And so we really didn't make any approximations. What we did is we looked at the geometry of our guide, and that let us simplify Maxwell's equations. So we're going to end this now with some final notes on implementation that I think you'll find helpful. The first is how we're going to set up our grid. So we're going to have a grid in memory, and here's the edges of the grid outlined in black. We're going to build our waveguide, whatever that might look like, in the middle of that grid. But what we need to do is put some space between our waveguide and the edge of the grid. So all the energy should be confined to the guide, but some energy may stick outside of that, but we know it's going to decay exponentially. We need to have a wide enough spacer region so that none of that energy or power touches our grid boundaries. We're going to be making a Dirichlet boundary condition approximation here. So if the fields are not zero by the time they get to the boundary, well, we're going to force them to be zero, and we're going to get a slightly wrong answer. So here's a really good example. Here's a simulation of a guide where we have a huge spacer region, probably too big. We could maybe bring the edges to about here. But you'll notice that the field isn't touching the boundary, so we're going to get a very good answer here. Well, what if we don't do that? What if we bring these edges in too close to the waveguide and we calculate the same mode? Well, this is what comes out. Now, isn't this crazy? We have a symmetric waveguide in a grid, and suddenly the field looks like it's being sucked to the lower left. So I won't answer this question, but I'll pose the question: why in this symmetric model are the fields suddenly asymmetric and being sucked off to one corner? I certainly know the answer to this, so if you have that question, please pose that to me. If you're curious, hopefully you will be. Here's a summary of our formulations. We started off with the full vector analysis, no approximations there. We can analyze anything from microstrip transmission lines to rib waveguides and integrated optics. We found that it is a good approximation to do quasi-vectorial analysis rather than the full vector analysis. We made some approximations there. So we went from having one big matrix or eigenvalue problem to having two smaller ones. And in fact, it buys us some speed and efficiency. Then for slab waveguides, it's simplified even further. So waveguide analysis, we use finite differences and matrices and linear algebra to construct these eigenvalue problems, and then we solve it in one line of code in MATLAB with Eig. And so here's how it works. You'll have an A and B matrix, which comes out of the matrix equation. You should be able to build those, but it spits out eigenvectors and eigenvalues. So here's what these matrices look like, the way we formulated it. The columns of the eigenvector matrix are our modes. If we plot these, we're going to see pictures of our modes. The eigenvalue matrix, remember our eigenvalues were that propagation constant squared. So in fact, they come out looking like this, the way we formulated it. But for every eigenvector, there's a corresponding eigenvalue. These are pairs and have to stick together. This is a picture of the mode. This is a description of how it propagates. So eigenvalues tell us how it propagates. The eigenvectors tell us what that envelope looks like. So if we were to do this graphically, we can envision our eigenvector matrix looking this way, where the columns are our modes, and if we plotted them, we would see our modes. And we can overlay that onto the original slab waveguide, and we see that the modes correspond to where the guide is. So when we calculate an eigenvector matrix, think of the columns being this way. Now, you're probably going to have hundreds of columns. I'm only showing 5 here, but it illustrates the concept. The matrices that we construct are sparse. So in fact, we can use another eigenvalue solver in MATLAB, Eigs, with the S. So this is a sparse eigenvalue solver. And this lets us do some neat things. Rather than solve all possible modes, we might know ahead of time that our guide only supports 3 or 4 modes. Maybe we're not exactly sure. So we'll just solve for the first 12 modes. And that's much faster than calculating all potentially hundreds of modes. So the way this works is we'll have our omega squared as our first input argument, the number of solutions that you want to obtain, and then we can also give it a guess for our eigenvalues. And in fact, it's going to calculate all the modes with an eigenvalue closest to the guess that we gave it. So how do we do that guess? Well, we have to go back and remember that gamma squared is our eigenvalue, and we related it to the effective refractive index. So the effective refractive index in a dielectric waveguide is going to be very close to the refractive index within the core. So this is a really good guess for our eigenvalue. It may not be perfect, but it is a good guess. Now when we actually get the eigenvalue gamma squared, here's how we would calculate the actual effective refractive index from it. It's going to come back as gamma squared. We'll take the square root of it. So really we're just left with gamma, and we multiply it by negative j because gamma is going to come back being imaginary, and we'll have our effective refractive index. Last slide. A little bit more on calculating the effective refractive index. Our eigenvalues come out as gamma squared, and we'll have a gamma squared for each mode that we've asked it to calculate. So we'll take the square root of it. So we're left now with just the normalized propagation constant. We'll multiply by k0 to unnormalize it. We're going to realize that this is a complex number. There's an alpha and a beta. The alpha is going to describe attenuation. The beta is going to describe oscillation or wave propagation. So the real part's alpha, imaginary part's beta. The beta, our ordinary propagation constant, is k0 times the effective refractive index. So we can combine all this and come up with a way to calculate the effective refractive index straight from gamma squared. We're going to take the square root of it and take the imaginary part of it, and that will be our effective refractive index. And so that's it. That is waveguide analysis, and we're not going to implement this in this class, but this set of slides is comprehensive in that you should have everything you need to do the analysis.